Lab 3, Black Hole, Richard Morin. Introduction Instructions. This lab was broken into two parts, with part 1 being to find the mass of the black hole in a black hole and star system, and part 2 being to find the initial velocity of a spaceship in a system including the black hole from part 1 and a planet. Both of these parts were to be done using a code, which was given to us and which we were to alter. Introduction Purpose. The purpose of this lab was to determine the mass of the black hole of the system in part 1, and then determine the velocity required of a spaceship such that it approaches the black hole but still escapes it in a system that also includes an orbiting planet in part 2. Overall, this relates to a larger purpose of understanding the physics principles behind the concept of gravitation and forces, specifically relating to force parallel and perpendicular. Results Preview. Through this lab, it was determined that the mass of the black hole is 1.31274 times 10 to the 34 kilograms, as in part 1, and the velocity at which the ship can approach the black hole but still escapes is 1,400,000,000 meters per second, which is simulated using an altered version of the code provided in part 2. Models and principles. So the main principles used in this lab were Newton's second law, being that force is equal to a change of momentum over time, F parallel, which is equal to a change of momentum over time times the unit vector n hat, F net is equal to F parallel plus F perpendicular, the position update formula as provided, and the velocity update formula as provided. So the rationale. Newton's second law was used to evaluate the forces acting upon the systems in each coding situation. The equations for force parallel and perpendicular were used to determine the breakdown of the total net force, providing valuable insight into the systems. The velocity update formula was used to find the velocity of objects in the system, and the position update formula uses the velocity from the velocity update formula to find the position of objects in the system. So systems and surroundings. So in part 1, for each system, in part 1, the black hole and the star were the system, and in part 2, the black hole, spaceship, and planet were the system. For the surroundings were every other object within the context of the problem that is not included in the direct system. All other objects in space, not included within the scope of the calculations. Listed here were the initial conditions for each part of this lab. In part 1, we receive a gravitational constant. The mass of the star was 2 times 10 to the 30. The delta T was 1 Earth day, which was 86,400 seconds, and the time for the first observation data point was T is equal to 0. For part 2, the mass of the black hole was provided, as found in part 1, which was 1.13421 times 10 to the power 39. And then it also included were g, the gravitational constant, the planet mass, 9 times 10 to the 28, the ship mass, 7 times 10 to the power 10, the delta t, which was 1 second, and the initial time, t is equal to 0. Also included here was the maximum time to run the simulation, which I used t max is equal to 60. So now on to the coding. So as seen here, this is my code. Important lines include F net, which is equal to the change of momentum over change in time, and also p hat, d mag, dp, pdt, and change of momentum parallel and change of momentum perpendicular. These values were all used to find the mean mass of the black hole, which is 1.13421 times 10 to the power 39. The importance of this value was that it was to be used in the coding part 2, which can be seen right here. Through this code, as shown, I was able to calculate a trajectory for the spaceship that approached a black hole while also escaping such. This can be seen by the image on the right. The potential errors of these codings. So slight errors in the calculation of a mean due to the amount of iterations run could have occurred, as more iterations will provide a more accurate mean mass for the black hole. This is most evident in problem 1. The second potential error was potential errors in the coding of the problem. There may be errors in my coding that I may not have been aware of, which could have led to slight variations or slight inaccuracies in my values. And finally, rounding. Rounding limits the scope of the numbers, meaning that some calculations might not be as accurate as they could have been if there was no rounding. In relation to this what does it mean question, net force is equivalent to a rate of change of momentum over time, and this corresponds to the net force parallel and perpendicular once the unit vector is applied. The net force parallel dictates speed, while the net force perpendicular dictates direction. In regards to this what-if question, the spaceship should have a velocity that counteracts the force due to the planet and the forces due to the black hole, but is not great enough to leave the orbit of the black hole. This is specifically in relation to net force perpendicular. In conclusion, overall, both coding models worked. In part 1, I was able to determine the average mass of the black hole over the time steps evaluated, being 1.13421 times 10 to the power 39 kilograms. In part 2, I was able to simulate a system in which the spaceship approaches but does not collide with the black hole, being a speed of 1,400,000,000 meters per second. Thank you.